So in a radioactive decay model, like we talked about, the concept of half-life comes up. So the half-life of a radioactive isotope is the amount of time required for the sample to decay to half of its original size, regardless of whatever that original size was. And this will always be the same factor. So the idea behind radiocarbon dating is that you can measure the amount of carbon-14 locked into an organic sample. So the idea being here is that while the organic sample was alive, whatever it was, a tree or a hominid or whatever, um, there was a certain amount of carbon-14 circulating through the atmosphere, and that amount is being regularly infused into the tissues of the organic creature. When the creature dies, however, at that point there's no new amount of carbon-14 coming into the system, and whatever's there begins to slowly decay. And by slowly, I mean that it has a half-life of 5,700 years. So if you measure the amount of C14 present in a sample, you get some idea of how long ago that organism died. So let's see. So in this case, if we're looking at radioactive decay, then say we start with P naught atoms of whatever radioactive material it is, then the birth rate is 0 because these particles don't spontaneously become radioactive isotopes. But we do have that the decay rate is going to be positive, that the time rate of change of the population is going to be minus delta times p, and by solving this equation like we've seen before, we end up with the amount at time t is the initial amount times e to the minus delta t. Okay, so let's consider an example, and we'll look at Stonehenge. And say we've got a charcoal sample, and the charcoal sample has 63% as much radioactive carbon-14 as a present-day sample. Okay, so given the half-life of 5,700 years, we can find the rate delta. Okay, so let's see. So how do we do that? Let's let t equal 0 be the time when the tree was killed. And we assume that it died relatively soon, or at relatively close to the time that it was used for firewood. Okay, so let's see. Then the equation that we have is 1/2 of p is going to be p evolved forward in time by minus delta times 5,700. Okay, so we can, let's see, so first I can cancel those p's, and then I can take logs of both sides, and so the log of 2 is going to equal delta times 5,700, and so then that means that delta is going to be it's going to be log 2 over 5,700, which is approximately 0.00 1216. Okay, and let's see now. So now to find t, let's see, so 63% of the original sample, that's supposed to be the amount that we have, but if we looked at what was evolved forward according to the model, so it'd be e to the minus, and now we've got this parameter, we know that it's log 2 over 5700 times t, and so that means that our time t is going to be minus log 0.63 over log 2 times 5700. And by the way, if this right here makes you nervous because it looks negative, realize that 0.63 has a negative logarithm value, so that entire quantity in the parentheses there is actually a positive number. And so our time comes out to being around 3,800 years ago. And so that tells us that the Stonehenge campfire was at around 1800, circa 1800 BCE.